Okay, so last class, we introduced the concept of SVD, right? We just stated a theorem saying, there's this magical thing called singular value decomposition, and that really says that, for every matrix, you can factor it in a very nice way as U sigma V transpose, where each one of them has some nice properties. Okay, and it also turned out that SVD magically solved the best fit subspace problem and the low rank approximation problem, right? It was a one-shot solution to both of these seemingly very different questions, which we've been kind of working with for the last few lectures. Okay, and finally, we talked about how to compute the top singular vector right? The top singular vector meaning the first principal component of the singular vector corresponding to the largest singular value sigma 1. Okay. And what we are going to do today is to try and understand why the thing that we do works and how fast does power iteration work, right? And then we'll discuss some extensions and connections of power iteration to gradient descent. And then I'll say some remarks on the variance of power iteration. And finally, we'll see one more application to matrix completion. An even better application than just directly applying low rank approximation, right? When we discuss matrix completion, the Netflix challenge, we said one approach is to just put zeros for the missing entries after you center them and use the low rank approximation as your first guess, right? And we'll build on power iteration to do something better later on, okay? And let me also mention assignment 2 is due today at 10 p.m. And as I said on EdSTEM, I'll be on a flight from 6 p.m. to 10 p.m. or so I won't be able to answer any last minute questions. But one thing I want to say is problem 3 seems to be harder than I anticipated. I'm seeing a lot of questions about it. But as I said at the beginning, there's always ample partial credit. So even if you don't get the full analysis right, as long as you get kind of the right algorithm or something like the right algorithm with the right intuition, you should get at least 80% of the credit for the problem, even if the analysis is not good. Okay, it can be only be more than that. All right. Okay. Okay. So now let's get to the lecture. So let's do a quick recap of what the power iteration was doing. And we got somewhere, but I want to rewrite it a little bit in a way that is more convenient for implementation. Right. So power iteration. Right. So what's the goal there? You're given an input, a matrix, n by d, and typically, just think of n being bigger than d. Otherwise, you would do it slightly differently. So always think of it being a tall matrix. And what is our goal? Our goal is to compute a vector v, right? The first right singular vector, the first principal component, or vector v that maximizes x times v subject to norm of v being 1. Okay, this is what we want to do, and we'll say, okay, we'll get close to it. And we're not going to say, okay, you'll exactly solve it, but we'll get close to it. And what was the algorithm that we said we're going to look at? Well, maybe I can actually copy this. Okay, so this was a power iteration algorithm. Okay, and remember, Y itself was X transpose X. Okay, so once again, how should you compute this matrix times this vector? Should you multiply these two matrices? No, right? Because that's way too expensive, unnecessary. So the way you write it is this way. Okay, so recall Y is X transpose. Okay, and the other thing is what you're doing here is I'm multiplying with this matrix again and again, and I'm normalizing at the very end. Okay, and this could be terrible in practice because every time you're multiplying, you might be increasing the norm by a factor of 2. You do it 100 times. You might end up with numbers of the magnitude 2 to the 100, which you then have to scale down by 2 to the 100, right? So you'll run into precision issues. So what would be a better way or more sort of stable way to implement the same algorithm? Yeah, normalize after every iteration, right? And why do you have to defer it till the very end? You only need to do it at the very end, but doing it at the very end only would be problematic because of the rounding errors, right? So you'll say, okay, let me actually do, maybe I'll call this vector VT double bar, and VT bar is just okay. Let me, this thing is getting too annoying. So let me call this vector UT, and VT bar is okay. It's the same algorithm as before, just that I'm normalizing every time so that I don't run into these rounding issues. And then you output. You don't have to normalize that. Okay. So we had some good intuition for what this algorithm should do, right? We said, okay, if there's a gap between the first and second singular value, like maybe one is 1, the second one is half or 0.9, then as you keep doing power iteration, the contribution of the others should go down, right? And it seemed like it was going down reasonably fast, but how fast? Okay, as it turns out, we can actually, prove a very precise rate of convergence. Okay, first, power iteration will converge to a top right singular vector. Okay. And what's the problem that we're trying to solve? We're trying to solve the problem of maximizing this X times V, right? And if you knew the SVD, what would be this maximum? Singular value, right? It's sigma 1 actually. So, I mean, we don't know what the value of sigma 1 is, but as a benchmark, that's what we're shooting for, right? So how well does power iteration do if you run it for t steps? What can you say about it? Okay. And what you can say is something actually very nice. So if I run it for if I run it for these many iterations, log of d over epsilon by epsilon many iterations, then the vector that you have at the end of these t iterations is a unit vector, and it almost maximizes x times v. Okay, the true maximum is sigma 1. You're getting epsilon close to it multiplicatively. Okay, so the order of convergence is like 1 over epsilon if you ignore the log dependence. Okay, does the statement make sense? Right, so you're converging to the true maximum. At the rate, if I want to get to 99% of the true maximum, then maybe I have to run like 100 iterations. In practice, typically, in fact, it runs even faster. Okay. This is like almost a worst case bound, but typically you can do even faster. And we'll see why in a little bit. Okay. So let's see why this is true and how one might approach this question. And we don't know the singular value decomposition. That's why we're doing this. But in our proof, we can imagine we have it, try and compare what we are doing to the truth, and then see how well we converge to it. Okay, so suppose that this is the singular value decomposition of x, right? And the singular values are sigma 1 greater than or equal to sigma 2, greater than or equal to sigma 3, and so on. Okay. And so one thing that we have to be watchful about is it could be that sigma 1 equals sigma 2. There need not necessarily be a unique maximum. If you take the identity matrix, what are all the singular values? 1, 1, 1, 1, 1, right? So everything is actually 1. Everything is a maximum, right? In that sense, it's not as if there's a unique maximal singular value. There's no unique maximal singular vector. Okay. So, and proceeding along those lines, it could be that the sigma 1, sigma 2, and so on, they're all very close to each other, right? I'm just kind of drawing the lengths here. This is sigma 1, maybe. This is sigma 2, and they keep decreasing. They could not decrease too, that can also happen, but let's just say they are decreasing. All right. And if this is the guarantee that we're shooting for, like I would only want to be 1 minus epsilon off, it might be okay for me to give the first vector or the second vector, so on, as long as these values are close to each other. Right? If sigma 2 is actually 1 minus epsilon times sigma 1, I'm happy even if you give me the second principal vector, right? Because it's still approximately just as good. Okay. So, I mean, if many of these are close, what should you look at? Well, let's look at the first value which drops below the target accuracy. Right, this is our target accuracy, 1 minus epsilon. Let's look at the first value where it kind of drops below that. Maybe this is the point where, let's say this is sigma k, this is sigma k plus 1. They're all decreasing, but at some point, they drop below 99% or whatever accuracy that we're shooting for. And let's let that index be k. Until here, they're all very close to each other. Maybe they're all actually equal to each other. So if that's the case, we should be happy with any value here. Right? We should be happy with any vector which is kind of in there. Okay. Any questions about this? And the power iteration will actually, if these are all very close, it won't distinguish between them until much, much later. Right? So let Sk be the span of the first k singular vectors, v1, v2. Actually, maybe k could get confusing, so let me denote this with m. Okay. So all of these things have singular value, which is very close to the first singular vector, sigma 1. So in fact, any of these would be good enough for the target accuracy we're shooting for. And even anything in this span would also be good enough. Okay. So that's why if I have something in the span, also I'm fine. And what we'll show is the following. If I run the power iteration for some number of steps, something nice happens. In particular, if I run it for t, which is roughly log d or delta or epsilon iterations, then vt bar is almost entirely in SN. Okay. So you run it for these many iterations, the vector that you end up with is in the span of the top singular vectors. We don't know which one it's going to pick because all of them are equally good for us, but it's going to be within their span. All right. So in particular, if I look, so how can I quantify the statement it is almost within the span? We can look at how much of the projection is in the span, right? So if I project this vector, the error is very tiny, it's at most delta. Okay. Any questions? Okay. So as you repeat it, you're making progress by converging to one of the top singular vectors by being in their span. And as stated, this is actually not correct. And the reason is the initialization. Okay, so here we pick the initialization to be the vector with the first direction, right? But what if your matrix is somehow something like this? Has the first row and column to be 0. And then there is a bunch of stuff. What happens in this case when I multiply it with the vector 1 and all zeros? If I multiply this matrix with 1 and all zeros, what do I get? I get this 0 vector. Okay. So clearly, power iteration doesn't satisfy the magical thing that I was saying here. It goes to 0 and then it gets stuck at 0. It's not going to do anything after that. Right. So was I lying all along, or is there a way to fix this? Any suggestions? Yeah. Right. But you don't know exactly what to pick. Right. And okay, so maybe we should go back a step and try to figure out why we chose this vector in the first place, right? So the intuition we had was, y to the L, the matrix should converge to this rank one thing, right? And where every column is proportional to the top singular vector, and then we wanted to extract something from that. If we look at a single column, maybe that column we get unlucky and it becomes 0, right? But all of these are along direction V1. So if you want to stop being unlucky in this case, you can just take like a random combination. Okay, so you're somehow, this is something you even do in various optimization, right? Don't initialize from a fixed point, because then you might be in a very unlucky scenario. So instead of that, let's just say you initialize with a random unit vector. Okay. So as a starting point, pick a vector which is random. Don't start with something like 1 and all zeros, because if you're unlucky and maybe that thing is actually in the kernel, then you would be in trouble. But if I'm random, then I can avoid such a thing. Okay. Right. So that's the fix. And now everything more or less solves. After so many iterations, with high probability over the randomness, in fact, this is okay. And more precisely, what we will show is the following. If I run power iteration for t steps, then how close are you to the span of the top vectors? You get close exponential. Okay, so remember this epsilon is something like 0.01, but you are converging at an exponential rate. Every step gets you a hit of 0.99 on the error. Okay. And there's a denominator here, which is the initial correlation of as long as you didn't get very unlucky and your first starting vector was completely perpendicular to the direction that you started out with, that you are going towards, you should keep making progress. Again, that's why random gives you something, because if you're random, the chance that this is 0 is very, very small. All right. Any questions about this statement? We're saying that every step gets you a little bit closer at this rate of 1 minus epsilon multiplicative factor per step. And we say this 1 and 2, theorem 2 implies theorem 1 by setting if you set it to be like this ln of something, then oops. Everything works out. Okay, if you set it to be this ln of something, then it will multiply here, and the epsilon will go out. You'll get epsilon. Okay. If I pick a random vector, you will have some correlation with any fixed vector, and the correlation should be something like 1 over square root d. So you will be fine. Okay, yeah. Yeah, you can take any column, but you don't know which column to pick, right? So it's better to just choose something at random, and that usually does quite well. Maybe sometimes you might pick a better initialization point, maybe if you have some slide information, but random is usually good enough. For the random thing, yeah, so that requires some concentration bound. But basically, this is standard fact in like high-dimensional geometry, where you say if I pick a random vector, then each of my coordinate is roughly 1 over square root d. It's a unit vector. Sum of squares should be 1, and all of them are like equally good. So each coordinate will be roughly 1 over square root d. Okay. Yeah, you can prove that, but we're not going to do that. But at least if I give you this, then theorem 2 should imply theorem 1, right? Because then you plug in root d, plug in the t, and then things would follow. Okay. So just as a calculation, okay, I mean, you can do better, but let's not hurt it. Okay. And more generally, if you plug in like this delta here, you get an even better bound. If you put in delta, then the same calculation gives you something nicer, which is essentially there's a lot of slack here, so we don't have to be very precise. We're only interested in the order of the bound, not the precise constant. So it's okay. Okay. Any questions? All right, let's see how we can prove such a thing. And what I'll do now is not actually prove the full theorem. I'll do a special case and you will extend it to the full theorem in homework. So what I want to do is, okay, there are two things here, right? We said, okay, you have to go as far as, the first singular value, which is less than 1 minus epsilon times sigma 1, right? We had to go up to this level. Until then, everything is equally good. Okay? But let's say we are somehow lucky, and let's assume that sigma 2 is actually small enough. Okay. Let's work under this assumption that the right index, where you drop below this threshold, is right away. The second one itself is smaller than 1 minus epsilon times sigma. Okay. So in this scenario, there's actually a unique solution that you should look for. You should look for something like V1, because anything downwards is not good enough. All right. And so in this case, what should the statement be? The statement should be, so m equals 1, right? Because the second one itself is smaller, and the first one is actually sigma 1, so m equals 1. So we need to show that the second one itself, there's a gap. So there's a gap between the first and the second singular values. Then after t iterations, the vector that you have will have almost all of its weight along the first principal singular vector. In particular, its projection with the first singular vector will be very close to the entire vector. Okay. All right, this is what we are going to show. Let's work in the easier setting where there's a gap immediately after the first one. And in this setting, you're actually going to converge to the first singular vector or the first principal component pretty fast. Okay. So the proof of this is the following. So, I mean, in some sense, all we get to do is look at what the power iteration does. Right, and this kind of should suggest, what was V1 bar? V1 bar was basically you multiply the matrix with the vector and then you normalize. Right, and right, these are the iterations that we have. Now I can think of this as, I'm sorry, this should be X transpose X. Okay, so this is the same as doing multiplying with X transpose X times. I mean, of course, we're not doing it in this order. We are multiplying it from right to left, but the operation is always the same. Where you multiply some power of the matrix X transpose X and then normalize it. Okay, that's what we are doing. So more generally, if you run it for some little t many iterations, you will have a power t here, you'll have a v0 as before, and then you have the normalization. Okay. So there's a numerator and there's a denominator. And what we'll basically show is that the numerator kind of converges to the first singular vector at some rate. And this is not too big. Okay. All right. And the proof carefully follows, it's almost the same thing that we did before. We just have to write down some things. Maybe let me review that as well. So we said X was U sigma V transpose. So we could write it as right. So writing X, we can also write it this way. And then we said X transpose X is the same thing, but with sigma I squares and only the V's. Okay, because the cross products go to 0. The cross terms go to 0 because Vi's are orthonormal to each other. Okay. And the other thing that we did last class was to show that if I raise it to the power t, then all of these singular values get raised to the power t and the vectors stay the same. Right? This is what we did. And this is what led to our algorithm in the first place. Right? Okay. So now what are we interested in, right? So we want to compute what does this powered matrix do on a vector V0. Okay. So X transpose X to the power T times V0. we want to understand what this does. Any suggestions on how we might approach it? V0 seems like a completely random vector. How can I quantify what this matrix does when applied to V0? Yeah. Right. Exactly, right? So the right singular vectors are actually an orthonormal set of vectors, right? So you can use them to write V0. Use that as a basis to write V0 as a sum of them. I mean, technically, you might not have all of the vectors, but you can add some other stuff if needed. Okay. So remember, there only are right singular vectors, but we can extend them to form an orthonormal basis if needed. Okay. Okay. So now what can I say? Well, I have this sort of weird looking equation. I have to multiply this matrix, right? I have sigma I to the power 2t with this vector. Oops. Okay. What happens when I multiply these two things? The same thing that we did before. This is a nice thing with orthonormal basis, right? When you multiply stuff, the cross terms will become 0 because they're perpendicular to each other, right? So if I multiply this technically, I had to multiply every term here with every term here. But V1 is perpendicular to V2 and so on. So all of those terms will become 0 and only the matching term will survive, right? So I will get okay, so this is what I will get. Because when I multiply with V1, everything except the first term will become 0. And for the first term, I'll get C1, and then V1 transpose V1 is 1 because it's an orthonormal vector. So it has unit form. Okay. All right. So even though it looked like a complicated matrix vector multiplication, it sort of simplifies, right? X transpose X to the T times V0. We have a nice succinct looking formula. Okay. And what are we interested in? We are interested in this vector, right? So the numerator is what we already have, and then we have to understand the denominator. Okay. So we want right? So this is the vector we are looking at, and we want to see how close is this to V1, right? So how close is this vector to the direction of the first principal component or the first right singular vector? And how can I tell that? What is its contribution to the first direction? Well, this is some vector, right? Think of this as some vector. And then my V1 is somewhere here. And I want to know how close is VT bar to V1. Okay. In particular, I want to know what is right? This is what I'm trying to understand. What's the length of, what's the error from the span of V1? But we've done something like this before. How can I calculate this length? Well, I know exactly what this is, right? So what's the length of this direction? It's given by the dot product between these two, right? So in particular, what is the dot product between VT bar and V1? Any guesses? Well, it's kind of written here, right? We are writing it in terms of the orthonormal basis. So the first coefficient will exactly tell you what's the dot product, because everything else is 0. Right? So V2, V3, and so on, they're all perpendicular to V1. So just looking at that should be enough for us. Okay. So this is actually equal to this normalization term, which stays as is, times okay. So we know exactly what the projection is, and then we can do some arithmetic to compute this length. All right. So it's easier to work with the square, and the normalization term, let's just keep it outside. Okay. So I have this vector x transpose x to the V0. I'm trying to check or compute the distance between that and the projection onto the first singular vector. But I have its representation in this basis, right? So what's the gap between what is this vector? Imagine I give you a vector, it has d coordinates, and I tell you what is the length of what is the error if I project out the first direction? I have a vector, let's say u1, u2 up to ud. And what is the error if I project onto the first coordinate? Any suggestions? Yeah. Yeah, which is onto the first coordinate. Yeah. Sum of squares of the other coordinate, right? You have d coordinates. I'm taking out the first coordinate because I'm projecting it out. So what is left? It's just sum of squares of the remaining things, right? So the answer should be u2 squared plus u3 squared plus so on. Okay, and then the square root because you're looking at the left, right? The same thing is happening here. This is an orthonormal basis, v1, v2, and so on. They're an orthonormal basis. And I'm saying, okay, project out the first thing. And what's the error going to be? Sum of squares of the contribution of the remaining thing. Okay. So this is exactly from 2 onwards now. Let me emphasize that. Same principle as here. And if I project out the first coordinate, what's left is everything from the second coordinate onwards, right? And here we're not doing it coordinate wise, but orthonormal bases are essentially the same. I'm projecting out the first vector in an orthonormal basis. So what's left is everything from the second coordinate onwards. Okay. And what are the contributions from the second coordinate onwards? It's all of these numbers, right? So I get sigma I to the power 4t times ci squared. Okay. Any questions about this? We've been using the orthonormality of the VIs a lot, right? And that's what makes this kind of analysis work. So that's why everything so far is nice equations. You don't have to do any inequalities or anything. Because we want to, the first singular vector, because we want to say somehow that it gets close to the first singular vector, right? And so we really want to say that the error from the first singular vector after projecting out should be very small. Okay, that means that you're converging to the first singular vector and we are happy. Okay. All right. So, so far we have like an exact equation. So let me summarize that. The equation that we have is okay. And we'll see later on in a little bit that knowing what makes this proof tick can actually lead us to better algorithms and how we exploit things. Okay. As I always say, we are trying to kind of prepare for the scenario where you have to tweak the black box algorithm in your own applications, right? And I'll give some use cases like that. Okay, but this is some progress, but we still have to do something. And we want to say that this error is very small. And the way we will do it is, you have a numerator and a denominator. We'll say the numerator is not too big and the denominator is not too small, so that the ratio remains small. All right. Okay. So let me do that. So there's a numerator which is and I'm going to use an inequality. What do we know about all of the singular values? They are, except for the first one, everything is smaller than sigma 1 by this 1 minus epsilon 5. Right? So we're working under the assumption that sigma 2 is bounded away from sigma 1. Right? There's a gap between the first and second singular value. Right? So you can, that is one starting point to try. So I'll say, okay. Good. I mean, some progress, getting simpler. All right. But what can you tell me about this guy? Sum of squares of the coefficients Ci. Well, where did they come from, right? So recall the way we got them was we said, V0 is a vector, it's of unit length. I'm then writing it in an orthonormal basis. Right? Yeah. Yeah. So in particular, it's at most 1. We don't even need that it's 1 minus the first one missing, right? We can just say it's at most 1. You projected a unit vector onto these different orthonormal basis directions. So this should be at most this much. Okay. So numerator, we have an upper bound on. And how about the denominator? So what's the denominator? You have this matrix vector product, and we are looking at the sum squared of its length. But we know what this matrix vector product is. You have it written up here. So what is its length? The VIs are orthonormal to each other, right? So what is the length of this vector? Yeah. Sum of squares of the coefficients, right? If I write a vector in an orthonormal basis, then its length squared is sum of the squares of the coefficients. So this is equal to which is at least the first term. It's sum of squares of many things. I'm going to say it's at least the first term, and that's good enough for me. Okay. And so the ratio is less than or equal to okay, so it is decreasing exponentially as t goes. And C1, what is C1? C1 is the coefficient of your starting vector, right? And if I have an orthonormal basis, I can compute the coefficient exactly, right? So C1 is actually equal to the inner product of V0, right? Because the way we got C1 was we say, okay, start with your vector V0, write it as in this basis of V1, V2, and so on. So what's the coefficient? Going to be the inner product of these. Okay. So what do we get? Equals therefore the length squared of the error goes down as this. So in particular, the length goes down as 1 minus epsilon raised to the power 2t divided by C1. Right, and this is what we wanted to prove in our corollary. Right, this is exactly what. Right? So the magic, of course, is to use the orthonormality of the V's again and again, because they're so. If you have an orthonormal basis, then all matrix vector multiplications and things like that become much simpler because the cross terms disappear. Okay. And this is for the case when you have a gap between sigma 2 and sigma 1, but you can imagine scenarios where that's not the case. Maybe sigma 1 and sigma 2 both are exactly 1, and then there is a gap. So in that case, what should you do? You can basically kind of do a similar analysis, just tweak it a little bit, and you'll get the answer. Okay. So we're not going to prove this theorem exactly, but we kind of put a special case where m equals 1. That there's a gap between just the first and the second. When there's a gap higher up, you have to do something else. Okay, any questions about the analysis? Yeah. So just to make the analysis easier, it's kind of an easier case to first get your hands on. So technically, that might not be the case, but at some point, maybe there is a gap. Even if there's no gap, you can do something similar. But if at some point there's a gap, then we have to work with not just one vector, but the span of many things. So just to make the first cut proof easier. Not necessarily, even if like in the identity matrix, right? But there also the statement is true because when there is no gap whatsoever, any vector is good enough. Like for identity, every vector is a singular vector. And that every vector x times v is just v. So the length is always 1. Okay. Yeah. So I mean, hopefully in the homework, I'll kind of give you hints on how to extend this to like multiple things, right? But the main thing I want to stress is the proof follows the intuition very closely. Right? We said, okay, x transpose x, when I raise it, somehow it's amplifying the first singular vector, and we're exploiting that and working with the same equation. Okay, you have a question? Yeah. Right. Yeah. So that's a very important question, and we'll talk about that in a little bit. Okay. So let's take a 5-minute break, and when we come back, I want to talk about that question, which is, okay, this is for the first singular vector. How about the second singular vector? And also about some other things that you can do on top of power iteration. Okay. Yeah. Let's pause for 5 minutes, and then we'll rest. Okay. So what we've done so far is compute the first singular vector, right? But before going to other singular vectors, let me say some further nice things about power iteration, right? Now imagine the following scenario. Some other nice properties. let's say I have matrices x1, x2, x3. And I want to compute the top singular vector of the product of them. Okay. If someone asked you this, how would you do it? Well, you can say I'm going to compute this matrix and run power iteration on it. But is that a good way? If I give you these matrices individually, would you just multiply it and run power iteration? Well, think of what power iteration does. Right? So to run power iteration, you need to be able to run this update. And we say we always compute it as something like this. Okay. Or what's a good way to compute this? Well, you should never multiply x out because I know that I gave you x1, x2, x3, and I'm trying to compute the principal singular vector of the product. If I plug it in here, I get okay. So what would you do? Right? You never have to even compute x to compute its first singular vector. All you need is the ability to do matrix vector multiplications with x. Okay. So imagine someone said, okay, here's a matrix. I'm not going to even show you what the matrix is, or you can't represent the matrix, but I'm going to give you a function handle, which will take a vector and return the matrix vector product with that matrix. Okay. So to compute SVD of x, we don't even need compute x. Let's say to compute first singular vector. Okay. Because all I have to do is kind of follow this chain, right? I'll multiply with x3 first, and then with x2, then with x1, and then do the same thing again. 3 matrices. These are matrices, right? Let's say this is n by n, n by n, n by n, and I'm just saying I want to compute the first singular vector of all of these things. I mean, you can imagine such a thing showing up, right? And if you have deep neural network, I have multiple weight matrices, and I have to multiply all of them. Why multiply? I can always do iteration one after the other. Okay. In fact, this is a very important primitive, and most sort of languages, especially the thing called LAPACK, which is a numerical linear algebra sort of package, which has been around for a long time, led to a Turing award and so on, for computing singular vectors and many of these things, right? And it has built-in support. So you don't have to pass in a matrix x to it. You can say, hi, here's a function handle, which takes a vector, computes a matrix vector product. As long as I can do that, I can compute the singular vector. Okay. So just need the ability to do matrix vector. Okay. This is an important thing in practice that you have to exploit in many scenarios. And then let's come to the next question, right? How to compute okay. Well, there are two approaches. One is more theoretically grounded, but the other one is, I mean, both are well grounded in theory, but one is easier to analyze but less efficient in practice. The other one requires a bit more analysis to prove, but more efficient in practice. So, okay, so let's go back to the singular value decomposition, right? We said we have something like this. Okay. If I give you, let's say someone gave you the first singular vector, what would you do? Well, we know that if we are given V1, we can find sigma 1 is norm of x times V1, and U1 is x times V1 by sigma. Right, so remember we had, sorry, x times V1 divided by norm of x times. We did this last class where we said if I know V, then I can find the sigma and the U. Right? The only thing that we need is V, and I can infer sigma and U from that. So let's say you do this, someone gave you V1, you can compute sigma 1 and U1. How can you find the second singular vector now? What's one natural thing you can do? Yeah? You can just subtract, right? If this is your representation, if I remove this, what's the first singular vector of the remaining matrix? It's going to be V2. Right? These are all decreasing order. If I knock this out, what's left? What's the top of, what's remaining? That's going to be V2, right? So technically, you can say to compute the second singular vector, you can say compute first of, x1 equals x minus sigma 1 U1 V1 transpose. Okay. And you can do the same thing again, to compute the third singular vector. What should you do? Compute the first singular vector of x2, which is the same thing again, right? I knocked out one. If I knock out the second one, what's left? What's the top? It's going to be V3. Actually, let me write it inductively so that it becomes clear. Okay, I can iteratively peel off one after the other and keep on computing the next singular vector. Right, and this is nice because it kind of comes from this representation, right? If this is the identity that I have, if I knock this out, then what's left is this, knock this out, what's left is this, and so on. Okay. So this is one way to compute the top k singular vectors, given you can compute just the first singular vector. Yeah. Right. So that's a good question. Like, would the errors propagate? And they do propagate, but fortunately, power iteration is strong enough. Right. Remember, it kind of gets this exponential closeness. So if you run it like reasonable number of steps, it's pretty good. In fact, when you implement it, as I said, typically within like 3 or 4 iterations, it just like shoots to the first singular vector as long as there's a gap. Okay. Even for something like the Netflix challenge data set, you don't have to run it like way many steps. Any other questions? Okay. That sounds good, but the one disadvantage of this approach is you lose some kind of, abstractness. Like imagine you have a huge matrix, but it is sparse, right? Then when I do the subtraction, I lose the sparsity. Take the Netflix dataset challenge, right? Take the Netflix challenge. There we said, okay, I'm going to build this matrix, which has 500,000 rows, 17,000 columns, about, I forget, was it 100 million? No, it's 1%, right? Yeah. 100 million non-zero entries, right? You can't store the full matrix, 500,000 by 17,000. If you think of it as a dense matrix, it's 8 GB roughly. You cannot store it in your RAM, or you can store it, but it's going to just like, make everything else like very slow. Whereas if you use sparse representation, meaning only store the non-zero values, that's like 1%, right? So it's 1% non-zero entries. So meaning if this is my X, I can compute X times V reasonably well without okay. Can you hear me now? Yeah. Okay, let's hope it only went away just now. Okay, so I can compute X times V reasonably okay, even though I cannot, like if I view it as a full matrix, I can't even store it in memory, right? So I can use this matrix vector multiplication to compute the first singular vector, right? But if I have to compute top 30 singular vectors, right? I said if you ran this SVD with the top 30, it gave you a 4% improvement, and it kind of plateaus after that. After that, you don't get any improvement. Then if I define x1 is x minus sigma 1 times u1 v1 transpose, this could be a dense matrix, right? So I cannot store this matrix fully in memory because it takes 8 GB size to store down. So what can I do? Is this method stuck then? Any sessions? So there are two cheats you can do. One is, again, remember, to run power iteration, you never need to know the matrix. All you need is the ability to do matrix vector multiplications. Okay. So my claim is that you cannot store x1 because it's the difference of like a sparse matrix, something which has 100 million entries as opposed to 10 billion entries. And this is a rank 1 matrix. So we can store that very succinctly. I'll just store u1, v1 separately. And then to compute x1 times v, I can do x times v minus Okay, so the same trick, right? I don't need to store x1. All I need is the ability to compute this matrix vector product, okay, which I can do efficiently. Okay, so if you were to do something like this for the Netflix challenge, you have to, you can't just say, I'll compute this difference and then run and then run the same algorithm. You have to be a little bit more careful. Okay, and there's another approach which actually is better, but I'm not going to say why that should work. And this is called the general power iteration. And the idea here is, so in power iteration, we're only keeping track of one vector at a time, right? In each iteration, I multiply one vector with x, transpose x, and then go on. But instead of that, in the general one, you try to compute all k at once instead of peeling them one after the other. So what you do is I pick k orthonormal vectors to start with. Let me call them, okay, there's going to be two indices. So let's say V01, V02, V0k. Okay. And then for each iteration, you do this. I define ut comma 1 is sorry. It's as if you are doing k different power iterations, but all in parallel. Instead of doing them one after the other, you're doing them in parallel. And as usual, we always compute them the right way. Okay, so that's the rough idea. Like, why should I wait for one to finish and then peel it off and do something? I can try to do them all together, but then you have to be careful because remember, the singular vectors should be perpendicular to each other. Right? That's the most important constraint that we have. And when you do this, you might lose perpendicularity. Okay, even if the V's that you started out with were perpendicular, after one iteration, they may not be perpendicular. Okay, so what do? You're an optimistic person, so I'll say, okay, I'll just fix it. So let VT1, VT2, so on up to VTK be an orthonormal basis for the span of okay. So you're doing a power iteration for all k in parallel, and then you find an orthonormal basis for them, and then do the same thing again. Okay, so this also works. It's something less clear from our analysis and so on, but you can show that this also works to find the top k singular vectors instead of peeling them one after the other. Okay, does the algorithm make sense? Yeah. So kind of, but the way you would implement it, I think it makes a difference. Like the way you write it is you'll say I'm multiplying X transpose with X. Sorry, this is X transpose. Then I have X, and then I have this V1 up to Vk. Right. So this product is going to usually be faster than doing column, column, column. right? It's a little bit like saying, if you're in Python, running the sum operation is faster than doing a for loop and adding up all of the elements in a list, right? And especially for matrix vector products or matrix products, it can give you reasonable boost. Okay, and I think that boost, kind of really helps over the other gains you might get. Right. So that's a good question too, right? It can be inefficient, but K is reasonably small. So again, you can do it in time, which is like linear in the dimension and like cubic in K instead of the other way around. So you can save something there. It's not a strict, like, this is always better than the other, but I think by and large, for large matrices, at some point, this method starts working faster. Yeah. Yeah, I mean, I think that's something that you have to do. Fortunately, this is such an important problem that people have optimized this to no end. Like, as I said, LAPACK is kind of crazy. The time I had to dig into LAPACK, this was in 2006 or 2007. It's written in Fortran, right? And so we had to like find an interface from MATLAB to C to Fortran, because it's so good. I mean, the package is very old, but it's still very good. It can multiply like this. It can. Back in the day, our memory was maybe 4 GB or something. Right? It could do these things reasonably fast. Whereas if you had to code it up from scratch, it would take us much more. Right? So they did a lot of optimization going into how do I do this matrix vector multiplication? What if I only have the handle and so on? So they were good. Okay, so there are a lot of optimizations that go into it. And in fact, let me say some other, this is not something that's like you can use, but you can imagine a theoretical scenario where this can show up. And there are some scenarios where you actually have to play with this stuff. Okay, so let me say something. So let's say X has singular values. Someone told you, okay, these are the singular values. The singular values are 1, 0.98, 0.97, 0.96, and so on. And X is symmetric. Okay, and let's say we can actually write it in this way. It has a nice sort of X is V sigma V transpose, meaning U and V are the same. So the singular value decomposition is extra nice. It's V, and then you have the singular values, which are 1, 0.98, 0.97, and so on. Okay. Now, if I try to run power iteration on this to compute the first singular vector, you're going to have very slow convergence, right? Because the gap is very small. It's like 0.02. So you have to run like 1 over 0.02 iterations to like get something. Okay, because the gap between the first and the second is very small. When the gap is small, to converge to the first takes much longer, right? But somehow, you can do some cheap tricks, right? So let's say all of these other singular values are 0.97. The first one is 1, the rest are 0.98, and something is like the rest are 0.97 or something. If I look at the matrix, which is X minus 0.96 times the identity, I'm subtracting a multiple of the identity from this matrix X. What are its singular values? Take a guess. I mean, exactly, right? So you're subtracting identity. Identity is the nicest matrix. So you have 0.04, 0.02, and then 0.01, so on up to 0.01. Yeah. Yeah. But identity is basically, any orthonormal set of vectors are singular vectors. So I can always subtract identity, and that only translates to shifting the eigenvalues. In this case, the singular values and the eigenvalues are the same. Okay? But again, as I said, it's a very sort of dummy example, but I want to illustrate what else you can do. Now what happens? What's the gap between the first and second? We didn't do anything. We just subtracted something, but what happened to the gap? 50%. You went from 2% gap to 50% gap. So if you run power iteration on this matrix, which is just as fast, you're subtracting something, that's it, with identity. So computing x times b is just as fast. But you would have to run 25 times fewer iterations because the gap is so much better. Okay. So you might wonder, okay, maybe if I find a right shift, I can speed it up a lot. And there are some tricks like this you can also do in practice. Okay. So singular values, and so the gap now is very, very good, right? So we should expect the power iteration on x minus 0.96 identity, which will converge to the same first singular vector, right? To run about 25 times faster. Okay, in fact, you can try and code it up and see too if you want. As long as the matrix is big enough, you'll see this boost showing up very easily. Okay, so there are lots of tricks like this. If you know the range of the eigenvalues, and people do the shifting operation, and sometimes there are ways to kind of shift it appropriately so that the gap gets amplified, and so on. Okay. All right. And one other thing I want to say is this is a part of theory that we are not covering, but there is a connection between power iteration and gradient descent, particular projected gradient descent. You can set up some cost function for some optimization problem and think of power iteration as basically doing some kind of weird gradient descent style thing. And if you can do gradient descent, what else can you do? What should you think of next? Stochastic, but also something else, where we consider variance of gradient descent, right? Let's say you're trying to speed things up. There is Nestrau, right? Basically add momentum. Okay. And there are algorithms like that too. There's versions called power iteration plus momentum. Doesn't give you as much of a boost typically as in plain gradient descent, but in some scenarios, it can also give you a reasonable boost. So here, I'll just kind of sketch the algorithm without any parameters. You pick a random unit vector. And for each iteration, you follow the same logic, which is right. So this is the power iteration step. Okay. Momentum just means that your update should not depend just on your current iterate, but also on the history somehow. Okay. So meaning you have to update it in some way depending on where you were in the previous step. So the algorithm looks vaguely like this. I'm not specifying what the beta should be and so on, but that's the rough idea. You don't take into account just the first update, but also take into account where you're coming from, and then do the update, and then you normalize. Okay. And theoretically, you can show that in some cases, PI has convergence rate something like 1/epsilon, right? We said if I want to get 1 minus epsilon of the maximum possible value, then I needed roughly 1/epsilon steps, right? That was our main theorem that we did not prove, but we proved a special case of it. Okay. And PI plus momentum is something similar to what happened in gradient descent, right? For gradient descent also, like it had a convergence rate 1/epsilon. If you did Nestrov's accelerated, you had a quadratic boost. You can get a quadratic boost for even for power iteration as well. But I think it's a lot more brittle. The assumptions have to be much stronger here. You need like the gap dependence is much worse. But again, I'm saying like in all of these things you can put together. Once you have a technique, you can bring back stuff from past, and like stochastic version is also important. Like sometimes you don't see the whole data set at once, right? Think of the columns, right? You have X and you have a bunch of columns and you only see some of them at a time. Then you have to update the singular vector on the fly, and there you might do something like some stochastic version, so on. Okay. And there are lots of other things that you can do. I want to do an application to matrix completion again, but maybe I'll do it in the next lecture. We don't have time in the remaining 3 minutes to do it. All right. But let me say that power iteration is like a very simple and important algorithm. It kind of forms the backbone of numerical linear algebra. And the reason we did the analysis is to know when is it like ultra fast, when is it somewhat fast. We now know because of the analysis that the convergence really depends on the gap between the first and the second, or wherever the gap is. If you drop from 1 to 0.99, it's not as good as dropping from 0.04 to 0.02. It's not the absolute value of the gap, it's the relative gap that matters, right? So you can play around with that to speed up your algorithms and so on. Okay. All right, let me stop there. And then next lecture, we'll start a new topic. Is differential privacy. And we'll also see how it connects to many of the other things. Yeah. Right. Yeah. So it's kind of a, yeah, there's some deep reason to do that. Yeah. So. Like any like is the most of them you're kind of no, you should think of it as like your gradient step, right? You move in the opposite direction to the gradient, right? So in that sense, like VT minus 2 is like the gradient. So okay, and yeah, so the parameter setting and everything is weird here. So yeah, sure. Yeah. Problem, the one with where you set the domain